Hello, this is Aditya, and this is my Physics 2211 lab report on constant velocity. The main purpose of this lab is to test Newton's second law in real life by observing the motion of an object moving at a constant speed without any change in its direction. We will compare the data obtained from the experiment to that of a computational model in an attempt to understand the Newton's second law even more. Here are some fundamental principles which are really important to understand this lab. Newton's second law of motion states that the net force acting on an object is always equal to the rate of change of its momentum, which can be written as F net equals change in momentum over change in time, which can also be written as mass times acceleration. Momentum is defined as the measure of an object's motion and can be written as the product of its mass and velocity. The momentum update formula Pf equals Pi plus F net delta t is used to find the final momentum. The position update formula Rf equals Ri plus V average delta t is again used to find the final position, and the velocity update formula Vf equals Vi plus F net over m delta t is used to find the final velocity. In the CloseScript code, we'll be using the momentum update formula, position update formula, and the velocity update formula accordingly. The assumptions for this lab is that there will be no air resistance. The experiment is done on a flat, uniform surface, and there will be no friction. It is also assumed that the calibration in tracker is accurate and quite reliable within the human error limits. The setup for this experiment is that a basketball is recorded moving at a constant velocity. The system in our case is the ball, while the surroundings is pretty much everything else like air, earth, gravity, etc. The video of the ball rolling is analyzed in Tracker to obtain a position versus time graph, and CloseScript is used to create a computational model. Some data from Tracker: the mass of the ball is 0.6 kg, the initial position of the ball is given by this vector, and the initial velocity is given by this vector. Here is a screenshot of the tracker setup. We can see the ball moving in the negative x direction, giving us the negative direction to the velocity, the graph corresponding to it with the values. Here's the code. We have taken the mass of the ball to be 0.6 kgs. We also defined the initial position of the ball and the initial velocity of the ball with the vectors. In the while loop, we have considered the F net to be 0. We also use the velocity update formula and also the position update formula to keep on updating the velocity and position for every iteration. Here is the data analysis. The orange line is the data from Tracker, while the green line is data from the computational model. As we can see, both the graphs are very similar, except for a few differences at the beginning and at the end, which will be explained in the next slide. So, why is my direction in negative? The ball, as I have said before, moves in the -x direction. That is why the velocity is negative, which is pretty much consistent with the coordinate axis in the direction of motion. But the speed, which is the magnitude of the velocity, stays the same no matter what the direction is. The signs only represent the direction the ball is traveling in. Why is there a slight difference in both models? As the experiment was done in a non-controlled environment, there's always a chance of error. In my case, the possible errors might be friction, air resistance, ball might be pushed too hard, and there's always a chance of human or application error in the tracker when analyzing the motion. The questions. So what happens if we flip the axis? That is, what happens in my case, what happens if I make the negative x-axis the positive x-axis? So in my case, if we flip the axis, then the direction of the velocity vector changes. That is, all the negative signs in my case becomes positive, but the magnitude, that is the speed, always stays the same. Is it possible for us to say how many pushes and pulls are being added together to give zero net force in the case that we have observed? It is not really possible to say exactly how many forces are being added to give us the zero net force. Yes, while we do observe the fact that ball moves at constant velocity, the experiment was still done in a non-controlled environment, and we can't directly say that the forces are balanced out to give us a zero net force. Thank you.